Hey guys, so I thought we'd just finish off oscillations by looking at damping and forced oscillations. So let's just go back and consider what we've looked at in the last couple of videos. So considering a mass on some frictionless surface attached to some spring, and we've been talking about the fact that it's going to oscillate backwards and forwards due to SHM. It's going to have some function. Its displacement function is going to go as either a sine 2 pi ft, and that's if we start it off at the equilibrium position here and give it some impulse, or it might be some similar cos function or something like that. And that's if we pull it to an amplitude A and release it. And we said so that's going to oscillate backwards and forwards between the positive and negative amplitude. And if you like, we sketched that graphically, and we said it would look like something like this. So if we've got some sinusoidal behavior going on, it will look like that. Not the best drawing. Let's just scoot this up a little bit. But one of the starting assumptions we made when we talked about this, was that we considered a frictionless surface, and obviously that's not physically possible in most, if not all, cases. So what we actually want to do is talk about what happens as some work is done against this oscillating body. So this is unrealistic, and this won't happen. So what will happen? Well, we know that if work done on the block occurs, we're going to have the block losing some EK into friction. So I'll call that W subscript F. It's going to lose some work to friction, and that means that less energy from EK is going to go into potential energy, because remember beforehand we sort of had this cycle backward and forward between these two. So energy was being passed backwards and forwards between potential energy in the spring, energy stored in the spring, and kinetic energy making it move. And remember, at equilibrium it was all here, and at the amplitudes it was all over here, and it was being passed backwards and forwards. Incidentally, what I didn't mention was it's this storing as a potential which allows SHM to change direction. We're passing all of the energy into our potential energy, which allows the mass to effectively change direction. Anyway, so what's actually happening now is there's some work done to friction in between, or not in between, I guess it's as an aside, and as it goes across here, let's think how to sort of denote this visually. So here's my work done to friction. As my EK is going across, some of it's going to be lost here, and as it comes back, some of it's going to be lost there. And as this goes round and round, this is going to continually happen until we reach zero energy, and all of our energy then is in work done against friction. So what's that going to look like? Well, obviously if EK is decreasing and EP is decreasing over time, that's loosely going to translate into the fact that its maximum velocity is decreasing. In terms of potential energy decreasing, that's going to translate in the fact that the displacement, the maximum displacement or amplitude, is going to decrease. Because if I've got less energy stored in a spring, remember energy is equal to half kx squared. So if k stays constant, the only way for EP to go down is for x to reduce. So at its maximum, if you like, at the extreme, that means the amplitude is going to go down. So we can draw that now, and it's actually an exponential function. The amplitude does decrease exponentially. So we can sketch this here. So whereas we had the amplitude being constant, now, this isn't the easiest to draw, but I'll try my best. Now we're going to have some function which is decaying exponentially. So we'll do this, something like that. And it will eventually come to 0 in real life. And as I said, this is exponential, so what we can do is we could draw a line through these maxima and minima, these amplitudes, and this would go as some exponential function. You don't need to know this, it would actually look like something like that, e to the minus, let's put in, I'll call that lambda, some constant, e to the minus lambda t, multiplied by the initial amplitude, then multiplied by the sine function that we had before. So this now would be our function for the displacement with time. So this would be equal to x. So it decays over time like that. And like I said, eventually what will happen is it will lose all of its energy and it will reach 0 again. I've not drawn that great. It will go to 0 down here, don't worry. So another thing we said is that v should decrease. Now we can actually tell from this that v decreases with time. Let's just zoom in on part of this graph just to make this a bit more explicit. So I'll just plot on slightly larger axes the initial couple of oscillations from here again, but I'll stretch them out and make them a bit more extreme. So it's gonna look something like, let's try again. Let's make this a bit longer. It's gonna look something like this. Okay, so a bit more extreme. And we can actually tell by sort of inspecting this graph that v is in fact decreasing. Now remember that v is distance over time, so loosely speaking, this is the gradient velocity, is the gradient of an xt graph. So we can look at the maximum velocity. We know v is maximized at equilibrium position, so x equals 0. And what we can do here is we can draw gradient lines. So there's one, there's another. Now you can see after one oscillation these start to decrease. This one's shallower, this one's shallower still. If this one could cross the axis here, it would probably be somewhat shallower as well. So each of these gradients, and again ignore the fact that these are changing direction, that's just because we've got this oscillating motion. These gradients should, okay, I've not, ignore this one, not drawn that one particularly well, but these gradients should be getting shallower. So if I just get rid of it all, if I look at the first three, they will actually get shallower. So that's a nice way to actually spot that. The final thing to look at with damping is that there are actually three kinds of damping that we're interested in. There is, so in red, if you like, if I just get rid of all this, this here is light damping. Let's pick another colour, blue. We can also have heavy damping, which will go from some maximum down to 0, so this is heavy. that doesn't oscillate, so it just goes exponentially down to 0. And let's get another colour, purple. And finally there is critical damping, which does something like that. So critical damping is the most unique, if you like. This is critical. Sometimes called overdamping because of the fact it overshoots my equilibrium. So critical damping is kind of like suspension on a car or something. When you hit a pothole, you'll feel that the car will sort of overdamp and then go straight back to equilibrium in the shortest time possible. So this occurs in the shortest possible time. And using again the example of cars, we want this to happen because obviously the last thing you want in your car is something like this, where you hit a pothole and your car is sort of oscillating for a long time. That's probably the worst thing you'd want in a car. So critical damping, probably the most important one to remember. It overshoots equilibrium, which you might consider a bad thing, but in doing so, that means that it can get down to 0, so completely stop in the quickest possible time. Heavy damping obviously is quick, but not as quick as critical, and then light damping usually is much longer because it oscillates back and forth. Okay, so that is damping. So the last thing to talk about here is our forced oscillations. So another thing we can do here is we might want to set up some system where we have our mass, we have our spring constant K, and we have some motor or some actuator here, which itself can oscillate backwards and forwards, and in doing so applies a force F to our mass, and it causes it to oscillate. So in doing that, we get some interesting physics. Obviously, if you grab something and shake it really fast, so let's think about this in terms of frequency. Because this thing is going to oscillate, it's going to oscillate with some frequency, which I'll call F subscript D for drive frequency. And that's going to cause my system to oscillate with some frequency F. Now, what I'm interested in is how does the amplitude of this system behave as I change my drive frequency. So we have this sort of interesting thing in physics where this spring system, because it's got some spring constant, if I just give that a little tap, it's going to oscillate naturally at some frequency. So we call that the natural frequency, and that's usually denoted by F0. So the natural frequency is just the frequency that it likes to oscillate freely at. So that's when you just perturb it, so you give it a little whack and then don't do anything else to it, and it will naturally oscillate at that frequency. You walk at your legs' natural frequency, so your legs act like penduli. If you push a kid on a swing, they will swing. That swing will oscillate at a natural frequency, and that's regardless of the mass of the kid you put in it. They will always oscillate with that same natural frequency. And this applies to everything. The noise that a glass makes when you flick it, that noise is oscillating at the natural frequency of that glass. And the glass example is quite good, so we'll come back to that in a minute. So that's the natural frequency. And what happens is we'll set this this drive frequency off, what I'm going to do is I'm going to start off at very high frequency. So I'm going to start off at this end of the spectrum, if you like, or this end of the frequencies. So what happens is, if I start my motor off and it's going to apply some force to my system, when I'm at very high frequency, that results in a very small amplitude, because if you like, I'm shaking it far too fast for it to do anything meaningful. By the time it gets over here, it's already been pulled back. So the actual amplitude is very small. But as I turn it down, that's going to increase, because I'm going to allow it more and more to oscillate. It has more time to actually do what it wants to do. So this is going to increase, and actually it will reach some maximum here, and that maximum corresponds to the natural frequency of my system. So I'll just draw that a bit neater. So here is my natural frequency, and it actually sort of peaks and levels off there. Things like to vibrate at their natural frequency. So when I give it a push at just the right frequency, its amplitude is going to get bigger and bigger and bigger. It'll just keep increasing. And we call this resonance. And resonance, by definition, is when your system is driven, so Fd is equal to F0. So my frequency is equal to my natural frequency. Amplitude increases to a maximum. So, going back to some of the examples from before, if you push a kid at the correct frequency on a swing, their amplitude increases. It'll get bigger and bigger and bigger, and if you carry on doing that enough, they'll eventually go all the way around, and that sends you back in time if you're not aware of that physics. So that's a good way to time travel. The other example with the glass, you all know about the example where you have opera singers, and they'll take a glass, a wine glass, they'll ding it, they'll listen to that sound, and they will sing a note at that frequency. And eventually what happens is the glass resonates, and it gets so high energy, those vibrations become so large, it actually shatters the glass, it breaks. So that's resonance. And we see it everywhere. It's not always a good thing. You've probably heard about the Tacoma Bridge, Tacoma Narrows Bridge, or the Millennium Bridge in London. They are examples where engineers haven't took into account the resonance of the structure, and in both cases, the Tacoma Bridge, the wind was resonating the bridge and it collapsed, or the Millennium Bridge, that was resonating under the footsteps of many Londoners and many tourists, and they had to close it and do some tweaks to change that. Okay, so what happens as we lower and lower our frequency? So obviously this is going to go down, but interestingly, you will want to say, Adam, this is going to go to 0, because when I'm not driving it, I'm going to have no amplitude. But you would be wrong in thinking that. What actually happens, interestingly enough, is this tends towards some non-zero number, and this is the amplitude of the drive. And there's a little bit more complex maths going on here, but the way that's easiest to think of this is, as you tend towards 0 in the frequency, you are still driving it. Doesn't matter how slow you do it. It might take you the age of the universe to do one oscillation, but you are still going to be oscillating this mass at the amplitude that your driver is moving forwards and backwards with. So it doesn't actually go to 0. So it'll level off at whatever that amplitude is. Okay, so again, just to recap, the important thing here is the fact that the maximum amplitude is reached at resonance, and that happens when if you remember, the drive frequency in hertz matches the resonant frequency of our system. By the way, some other things I could do, just while we're here, I could submerge this in water or something like that, and that would provide some extra friction, which would dampen this guy, and that means, as you remember, damping creates smaller amplitudes, so this would undercut this graph. It would have the same resonance, but it would always be below this graph. And likewise, I could lubricate the system. I could evacuate all the air, or I could replace all the air with helium or something, and that would create a higher amplitude, again at the same resonance. So if you like, this is less damping, and this guy down here is more. Okay, that's it. So that is Oscillations. In the next video, which should be coming as soon as possible, we're going to look at the frightening but interesting world of exponential physics and exponential relationships. Starting with some maths, I think, is probably the way to go. So, look forward to seeing you there. Thanks for watching. Cheers, guys.